In the last few lectures, we had analyzed or we had derived the conservation equation. Okay, for mass and energy, and for momentum, the Navier-Stokes incompressible mass and momentum equations. And they had the general form partial C by partial T plus the divergence of the velocity into C is equal to the divergence of d gradient of C, okay, where C was the concentration field and d was the diffusion coefficient and v is the velocity, plus any sources or sinks. And if the diffusion coefficient is a constant, this had reduced to d times the Laplacian of C plus S, okay, and a similar equation for the temperature. So, in this case, we have two terms, the time derivative and the inertial terms on the left, and the diffusion terms on the right, along with any sources or sinks. So, if you recall, in all of these problems, we had defined a scaled concentration depending upon the concentration that is specified, or the variation in concentration across the domain. We have defined a scaled concentration C star, okay, and we can also define scale length, okay, x star, y star, z star is equal to x by LC, y by LC, z by LC, where LC is the characteristic length. The characteristic length scale usually in the cross stream direction for the flow. And also similarly, there is a characteristic velocity in most problems. Okay. You can define the velocity components, okay, Vx, Vy, Vx star, Vy star, Vz star is equal to Vx by Vc, Vy by Vc, Vz by Vc. Okay, where Vc is the characteristic velocity. And if I express the equation in terms of this, right, what I will get is plus, okay, partial C star by partial T plus LC into Vc, okay, sorry, okay, the scaled divergence of V scaled velocity times C is equal to the diffusion coefficient by LC square, the scaled divergence, the scaled Laplacian, okay, okay, where the scaled Laplacian is defined as del star is equal to LC times the gradient. Okay, the scaled gradient is defined as LC times the gradient. Recall that the gradient operator has dimensions of length inverse. Okay, so you can write it scaled gradient operator as the characteristic length times the gradient. Okay. Recall that this is equal to Ex partial by partial x plus Ey Ez d by dz. Okay. And if I express this in terms of the scaled gradients, okay, I will get this divided by LC d by dx star, Ey by LC d by d by star, and Ez by LC d by dz star. Okay. So, in terms of the scale gradient, this is equal to 1 over LC times the dimensionless gradient operator. Okay. So, that is what I have substituted here. Okay. It has dimensions of 1 over length. So, if I multiply it by length, the characteristic length, I will get something that is dimensionless. Okay. And for the left side, for the time derivative, I can use the time scale as L by V, okay, where LC is the characteristic length scale and VC is the characteristic velocity scale. Okay. So, I will get here VC by LC. Okay. And multiplying both sides by L square by D, you get a dimensionless equation. Okay. Where this term here, this coefficient is the Peclet number. Okay. We have seen this earlier, okay, the Peclet number, and in both of these I forgot to put in my sources. So, let me just put that in, okay, plus S here, okay, and over here I will get plus S LC square by D. Okay. So, this will be a dimensionless source. Okay. This will be a dimensionless source. And as I was telling you, VC LC by D is equal to a Peclet number. And first we will consider the limit of low Peclet number, where the inertial terms can be where the convective terms and the time derivative can be neglected in comparison to the diffusion term. Okay. And when that happens, the equation reduces to what is called a Poisson equation, or del square C is equal to 0, which is a Laplace equation. Okay, it reduces to one of these. Okay, if there is a source or if there is no source present, it reduces to either a Poisson equation or a Laplace equation. Okay. And the method for solving this equation is exactly the same method that we had seen earlier for unsteady flows or unsteady transport in one dimension. That is the separation of variables method. Okay. The method that is used, the standard method that is used is the separation of variables. And I will illustrate this with two examples in a Cartesian coordinate system, and then I will proceed to looking at examples in a spherical coordinate system. Okay. So, the first example in a Cartesian coordinate system, okay, x, y, okay. I have a block of solid, okay. Okay, this is 0, 0, the origin, of length L in the x direction and height h in the y direction, okay, at steady state, and I have temperature T0 here on two walls. I have temperature TA at the bottom and TB on top. And what I would like to find out is the temperature field throughout the domain. Okay. What I would like to find out is the temperature field throughout the domain. How do I do this? Separation of variables. Recall that for separation of variables, it is first necessary to identify homogeneous boundary conditions in all directions except one. And that one direction in which the boundary condition is inhomogeneous is what is called the forcing direction. when we did the unsteady heat transfer or unsteady mass transfer in one dimension, in that case the homogeneous boundary conditions were in the spatial direction and the inhomogeneous term was in the initial condition, okay, that was forcing the difference between the actual temperature and the steady temperature. Okay. So, similarly, in this we have to find out two boundary conditions which are homogeneous, and the other two conditions are what will be the forcing conditions, which determine the departure from the temperature if there were only homogeneous boundary conditions applied. Okay. So, it is obvious here what we need to do. Okay. If we define the scale temperature or the reduced temperature as T minus T naught, okay, then we have boundary conditions T star is equal to 0 at x is equal to 0 and x is equal to L. Okay. So, this is T star is equal to 0 and here also T star equals 0. Okay. Okay. On the left and the right faces T star is equal to 0 because we have subtracted out the constant temperature at the left and right faces. T star is equal to T A minus T naught at y is equal to 0 on the bottom surface. Okay. So, I have two surfaces of equal temperature, okay, and I have a bottom surface that is at a different temperature and a top surface which is also at some other different temperature. Okay. So, over here T star is equal to T A minus T naught and T star is equal to T B minus T naught. Okay. Okay, and for ease of notation I will refer to this as is equal to T A star at y is equal to 0 and T star is equal to T B minus T 0, which is T B star at y equals h. Okay. Those are the boundary conditions. The heat conduction equation, okay, partial square T star by partial x square plus partial square T star by partial y square is equal to 0. Okay. Separation of variables, we substitute T star is equal to x of x star y of y star, where capital X and capital Y are some functions. X is only a function of x star, y is only a function of y star. Okay. Substitute that into the equation, divide throughout by x star times y star and you will get 1 over x star x, okay, d square x by dx square. Note now it is a total derivative because capital X is only a function of x star. Okay. I am sorry, it is only a function of x. Okay. I have not scaled the variable here, turns out you do not need to. Okay. Plus 1 over y d square y by dy square is equal to 0. This is what you get if you substitute x times y and then divide throughout by x times y. Now, the first term on the left is only a function of x, the second term on the left is only a function of y. That means that both of them have to be constants. What should be the value of the constant? Okay. We know that in the homogeneous boundary in the homogeneous direction, the solution has to have discrete eigenvalues and it has to have eigenfunctions which are in the form of orthogonal functions. For a Cartesian coordinate system, if you recall, those eigenfunctions are of the form sine of I pi times x by L. Okay. So, therefore, for the solution in the x direction, I have 1 over x d square x by dx square. This is the homogeneous direction. This has to be minus I pi by L the whole square, okay, which implies that x is equal to sine of I pi x by L. Okay. This function sine of I pi x by L is a solution of the equation, and it satisfies the homogeneous boundary condition, that is that this function capital X is equal to 0 both at x is equal to 0 and at x is equal to L for any integer value of I. Okay, so this is the solution in the x direction, and I have anticipated a few steps here. So, if I were to do it in long form, I would say that 1 by x d square x by dx square is equal to a constant. That constant has to be negative because it has to reduce to 0 at both 0 x is equal to 0 and x is equal to L. And for it to reduce to 0, right, there are two solutions: cos of a constant times x and sine of a constant times x. The cos function does not satisfy the boundary condition at x is equal to 0. It is satisfied only by the sine function. So, the sine function satisfies the boundary condition at x is equal to 0, and if the coefficient here is I pi by L the whole square, then the sine function also satisfies the boundary condition at x is equal to L. Okay. Okay. So, therefore, this is the solution in the x direction. Okay. What about the y direction? That, as you recall, is the inhomogeneous direction in this case, because the temperature field has a non-zero value at boundary condition at boundaries in the y direction. Okay, the temperature field has a non-zero value at the boundaries in the y direction. Okay. So, this was my original equation, okay, and I use this substitution. I will get 1 over y d square y by dy square, okay, plus minus I pi the whole pi L the whole square is equal to 0. Okay. And that will give us d square y by dy square is equal to I pi by L the whole square into y. The solution for this is y is equal to a e power I pi y by L. Sorry. Okay. Note that I is an integer here, it is not square root of minus 1. Okay. This I is an integer here. I am using I as separate from the square root of minus 1, which I will write as script I. Okay. Okay. I here is an integer, okay. It is not the square root of minus 1. Okay. Plus b e power minus I pi y by L. Okay. These are in the form of exponentials, okay, as you would expect. Okay. Therefore, T star has the form, okay, a e power I pi y by L plus b e power minus I pi y by L. Okay. The whole thing times sine of I pi x by L. This solution satisfies the equation for any value of I, because I have solved it in such a way that d square x by dx square and d square y by dy square times 1 over y, I am sorry, 1 over x times d square x by dx square plus 1 over y times d square y by dy square. The sum of these two is equal to 0 for this solution, a combination of an exponential and a sine function. Okay. If you just substitute this, you will find that the second order differential equation is identically 0. This also satisfies the boundary conditions at x is equal to 0 and x is equal to L, because this sine function is 0 at both x is equal to 0 and x is equal to L. So, this satisfies the homogeneous boundary condition in the x direction as well as the equation, okay, the governing equation, the Laplace equation for the temperature field in 2 dimensions. It satisfies these for any value of I. Okay. That means that the most general solution will be of the form summation I is equal to 1 to infinity of a I times e power I pi y by L plus b I times e power minus I pi y by L, okay, times sine of I pi x by L. Okay. So, this is the general solution. We have not yet satisfied the inhomogeneous boundary conditions at y is equal to 0 and y is equal to L. So, the coefficients will be determined from satisfying the inhomogeneous boundary conditions at y is equal to 0 and y is equal to L. So, what are the inhomogeneous boundary conditions? T star is equal to T A star at y is equal to 0, okay, which means that T A star is equal to sigma I is equal to 1 to infinity A I plus B I. Okay. When y is equal to 0, the exponentials are both equal to 1, okay, times sine of I pi x by L. Okay. The second boundary condition is T star is equal to T B star at y is equal to L. Okay. So, T B star is equal to summation I is equal to 1 to infinity of, in the exponential I have to substitute, this should be h. Okay. Recall that the boundary in the y direction is at y is equal to h and in the x direction it is at x is equal to L. So, this could be a rectangular block in general in which the sides do not have to be equal. So, the boundary condition has to be satisfied at y is equal to h. Okay. So, I will get A I times e power I pi I pi h by L plus b I e power minus I pi h by L sine. Okay. So, these are the two boundary conditions that we get. And now, how do we determine the coefficients? We have to use the orthogonality relation. Okay. We have already derived the orthogonality relation earlier. Integral dx from 0 to L of sine I pi x by L sine j pi x by L. When we had derived it earlier, we had scaled the x and y directions. In this case, I am not scaling it, I am just assuming using the dimensional distances itself. Okay. So, this you can use a trigonometric identity to write this as dx into half of, okay, cos of I minus j pi x by L minus cos of I plus j pi x by L. We had seen this before, I am just refreshing your memory. Okay. So, this I can write it as half into sine of I minus j pi x by L divided by I minus j. Okay. Integral of the cos function is plus sine function. Okay. Between 0 and L. Okay. And since I and j are integers, right, since I and j are integers, This term is identically 0 if I is not equal to j, because sine of an integer times pi will be equal to 0 and sine of 0 is also 0. The only non-zero value you have is when I is equal to j, in which case sine of this argument in the limit as it goes to 0 is equal to the argument itself. Okay. And I will get this as L, okay, from this term here. Okay. This I will get it as L, okay, from this term here, into delta ij by 2. Okay. L into delta ij by 2 is what I would get. Okay. So, this is non-zero only if I is equal to j. Okay. The left side of this equation, okay, was integral dx Ta star sine. So, let me back up a little bit. So, I have two equations here. Okay, I have two equations here. Okay. This is equation 1 and this is equation 2. Okay. Both of these are multiplied by sine of I pi x by L. So, multiply both of these by sine of j pi x by L and integrate from 0 to L dx. Okay. And the orthogonality relation that I have got for you are the right hand sides. Okay. The orthogonality relations apply to the right hand side. What about the left hand side? Okay. In the first equation, for example, on the left hand side I have had integral dx Ta star, okay, sine of j pi x by L, okay, 0 to L. Okay. This is going to be equal to Ta star into minus cos of j pi x by L divided by j pi by L between 0 and L. Okay. And this will be equal to Ta star into 1 minus, okay, evaluating this between 0 and L. At L, there is no 1 over L here, my apologies. At x is equal to L, the cos function is just j pi. X is equal to 0, the cos function is 1. Okay. So, if you evaluate this, you get 1 minus cos of j pi. Okay. And this can be written as L Ta star by j pi into 1 minus 1 power j. Okay. Because cos of j pi is 1 if j is even and it is minus 1 if j is odd. Okay. Cos of 0 is 1, cos of pi is minus 1 and so on. Okay. So, this I can substitute on the left sides of these two equations. Okay. This I can substitute on the left sides of these two equations and the two equations will become Ta star into 1 L into 1 minus 1 power j by j pi and Tb star L into 1 minus 1 power j by j pi. On the right side I have summation I is equal to 1 to infinity of Ai plus Bi into L delta Ij by 2, okay. L delta Ij by 2 because of the orthogonality relation here. Okay. And this one I will have summation I is equal to 1 to infinity of Ai e power I pi h by L plus b I e power minus I by h by L into L delta I j by 2. Okay. So, those are the right side from the orthogonality relation and the left side from just multiplying this constant by the cos function, the sine function. Okay. And since it is non-zero only for I is equal to j, I can remove the summation and replace I by j. Okay. Remove the summation and the delta function and replace I by j. Okay. So, this is h by L. Yeah. These two simultaneous equations can be solved to obtain what is AI and BI. Okay. And you can use that and substitute that back into the equation. You get AJ is equal to 2 into 1 minus 1 power j by j pi into TB star minus TA star e power minus j pi h by L, okay, by e power j pi h by L minus e power minus j pi h by L, okay, and Bj is equal to 2 So, this completely specifies the two coefficients A and B in this solution. Okay. It completely specifies the two coefficients A and B in this solution, and then you can plot this as a function of x and y in order to find out what is the temperature field. Okay. So, the important steps in this solution procedure, we are trying to solve the Laplace equation in a rectangular domain, and we had to identify one direction which is homogeneous. In this particular case, the temperature itself was equal on two faces. So, if we just subtracted out that equal temperature, we got T star is equal to 0, and we could identify that as the homogeneous boundary condition. In case you have a situation where all four temperatures are the same, you can choose any one direction as homogeneous by subtracting out from the temperature a linear function of x, for example, in such a way that Ta is temperature T star is equal to 0 on the left and right faces. Once you have that, use separation of variables, homogeneous boundary condition, the solution in Cartesian coordinates are sine and cosine, and the eigenvalues are I pi by L, where L is the distance in that direction. The other direction you solve it, in this case you get exponential functions in the y direction, and the coefficients are determined from the boundary conditions in the inhomogeneous direction, okay, as I had shown you. So, you have two equations for the coefficients at the two boundaries. Both those equations at those two boundaries at y is equal to 0 and y is equal to h, multiply by sine of j pi x by L, integrate and use orthogonality to find the coefficients. So, this is a simple extension of the separation of variables procedure for the diffusion equation in two-dimensional Cartesian coordinates. We will look at a slightly more complicated example of the flow in a rectangular channel in the next lecture, how to apply separation of variables to that problem. I will continue this in the next lecture. I will see you then.